right? Everyone give us a little like thumbs up, click accept to the record. Okay, so hi everyone. Thank you all for coming to our guest speaking event. We're very excited to have Vicky. I hope I say your last name right, Siegel. Siegel. Okay.
Yeah.
I was gonna say that one, and I was like, well, Vicky Siegel from Stone Aerospace. Stone Aerospace is based in Austin, Texas, and is a company dedicated to the exploration and commercialization of frontiers we know of, and the discovery of ones yet to come. Which is a really cool sentence that they have on their website. We're very thankful to Vicky and Stone Aerospace for taking the time to come and talk to us about what they do, how they do it, and most importantly, why they do it. Now for the main event, please take it away.
Yeah, hi, I'm Vicky. Let me see if I can figure out the screen sharing. Oh, I am disabled by screen
You're
sharing.
disabled. Multiple participants. Right.
It should say when you go to share screen, there should be like a little arrow to the top.
Now it will let me do it. Yeah. Okay.
No, okay, sorry.
Okay, and then trying to figure out how to make it work with the presentation mode in PowerPoint. Is
there we go. Can see something.
Yeah, I'm working on getting the slide going. Okay, does that look like just a presentation slide and like nothing else?
Nothing else.
Yes.
Perfect.
Okay. All right, awesome.
Okay, here we go. So my name's Vicky Siegel. I work with Stone Aerospace. I have for about 15, 16 years now. I wear a lot of hats there, but my business card says that I am the director of field operations, and I'm also involved in autonomous systems design. I'm going to talk about robotics for the ocean worlds, and I just wanted to say it is Veterans Day, so if anybody watching is a veteran, thank you for your service. So let's, as I was telling everybody, there's a lot of ground. I'm going to try and cover it pretty quick, and then we can dig into some details of whatever you guys have questions with kind of at the end or in the middle. Don't hesitate to interrupt me. Okay, so Stone Aerospace, it was kind of founded and continues to work a lot on building robotic systems for planetary exploration for NASA. And so there's kind of like a lot that's involved with that, but we're a small company. We've been around for, like I said, about 16 years, based outside of Austin. Kind of setting the stage. Let's see if I can move this little window where I want it. Okay. I'll start by setting the scene here and defining what an ocean world is. Since this is a robotics group, this isn't a planetary science group. An ocean world is any world with a liquid water ocean. Of course, Earth is an ocean world, but our solar system actually has several others. And the more that planetary scientists look for these things, the more of them that we're finding within the solar system. And we're finding that the moons of the outer planets, so moons around Saturn, Jupiter, Neptune, Uranus, may have liquid water oceans underneath icy shells. So why do we care? People care about ocean worlds because they may be one of the best places to search for microbial life off of Earth. And in particular, one of the most promising targets is Jupiter's moon, Europa. It's the sixth moon of Jupiter, first observed by Galileo. So Europa is kind of a crazy place. It's similar in size to Earth's moon, but it has a thick ice shell that might be up to, we're not sure, 30 kilometers thick. And then it has a liquid water ocean. And importantly, that liquid water ocean is in contact with a rocky core. So this is where people like astrobiologists get really excited that the chemistry might be there to support life. You have water in contact with rock. And that rock is tectonically heated as the moon is orbiting Jupiter, and that's what enables the water to stay liquid. Right now, we're really familiar with robotic missions to Mars. You see all these rovers running around on the surface of Mars, super cool stuff. If you look at extending that to an ocean world and getting where you want to go into that ocean, what is that kind of a mission look like? Basically, there are 3 phases in that kind of a mission. First, you need a lander to just get everything down to the surface. Then you need an ice penetrating robot, and we call that a cryobot. You need that to descend through the ice, and then you need that cryobot to ultimately deliver an autonomous underwater vehicle, an AUV, that can actually swim around and map and explore in a completely unknown environment with no navigational aids, and very, very limited communication back to Earth. There's no human in the loop in this system. So we've been working, Stone Aerospace, we've been working on the cryobots and the AUVs. So first we'll kind of dive into some of the cryobot projects that we've had. So I'm going to give a quick sampling of 3 different cryobot concepts and systems that we've been working through. And the place to start the conversation about ice penetrating robots in the outer solar system is the question of power. Spoiler alert, this mission is going to have to be nuclear powered. Solar is not sufficient in the outer solar system. Primary batteries aren't going to cut it either. So you're looking at some sort of nuclear power source. This is by no means my specialty, so I'm not going to go into the details here, but basically there are a couple ways to do this. They're shown here. For our purposes right now, though, developing kind of these system level technologies, we want to simplify our prototype development and all of the testing that we need to do. We want to do all of that without the complications that come with working with nuclear materials, of course. But we need the cryobot systems that we design to still be compatible with having a thermal power source instead of whatever would be most convenient for us. It'd be really convenient for us to throw some lithium batteries on there, but then it's not really realistic. So what's the point of doing the work? So we've come up with a couple of clever surrogate systems to kind of work around, not actually having our hands on nukes, but working with those thermal power sources. And the first way we kind of played with doing this was actually with a really cool high-powered laser. And basically what we decided to do was take a 5 kilowatt laser and send 5 kilowatts to an ice penetrating robot over fiber optic tether. So if you guys have seen these bare fiber optic tethers, they're super thin, super fragile, like little linguine noodles or something. The first cryobot that we did this was called Valkyrie. Essentially the way that Valkyrie worked is that the fiber optic carried 1770 nanometer laser light from the cabinet, this big refrigerator sized laser cabinet. The fiber carried that light into the lower part of the cryobot. And here that's kind of the black cylinder that you see here. That laser light then exited the fiber. It was directed through some divergent lenses. Those lenses spread that IR light over the inside of the cylinder that heated the cylinder up. The cylinder was a heat exchanger. We pumped water through the walls of that heat exchanger, and then we made hot water. Well, hot water is actually the best way to melt ice. If you have hot water and a high pressure jet, you can drill through ice very efficiently. This is what people do in the Antarctic when they're making very deep holes in ice. So we developed this whole system. We took it for 2 field campaigns on the Matanuska Glacier in Alaska. This is about 3 hours kind of northeast of Anchorage. So in the upper image here, you're looking at the mission control. Basically, that white tent is the mission control. It housed the laser cabinet. You can see that big kind of tan, white, beige colored 30 kilowatt generator there. That's what's powering the laser. Valkyrie was actually in the ice right now. You can see the little gantry that's there. It's empty, so Valkyrie was on a mission at this point. And then on the right, you can see 2 of our engineers, actually the company founder, Bill Stone, and our electrical engineer, John Harmon, inspecting Valkyrie as it's descending into the ice. Valkyrie was able to steer. So in addition to the main water jet that we had in the center of the nose cone, there were 4 steering jets that were offset from that by about a 5-inch radius, and differential jetting through those different jets allowed us to play with steering the cryobot as it goes down. So if you jet more on one side, the cryobot's going to kind of start to move. And you want to be able to do that because we don't know what's in the ice on Europa. There could be meteorite debris. There could be, brines and different minerals that create some sort of insoluble layer that we're not going to be able to drill through with hot water. So this idea of being able to maneuver through the ice is important, and we were able to accomplish it You can see the little 3-dimensional trajectory of one of the test runs of Valkyrie there. In addition to just getting through the ice, one of the conditions of the NASA grants that we typically get is that you have to develop some sort of technology to do some sort of planetary relevant thing. But then you also have to like take that thing that you just made and use it for real somewhere to do something, to collect some sort of data that's useful to a geologist or a biologist here on Earth right now. So with Valkyrie, we had a life detection and water sampling system kind of built in. So the cryobot carried a cytometer, that's basically a cell counter. And when the cell count in the meltwater spiked, because things live in the ice, actually, it's interesting to learn. But so there's microbes living within the ice. When that cell counter spiked, the cryobot would say, oh, hey, this is a great time for me to collect a water sample or a filter sample. And that's what all this tubing is that you see in that image. So skipping on to the next project, after all of that playing around with lasers, we wondered, well, you know, we've been doing this whole goofy thing where we run the laser light through the fiber, we shine the thing into the heat exchanger, we do all this stuff. What if we just, I don't know, did the Dr. Evil thing and shined the stupid laser light right into the ice? And it turns out that that actually works. We kind of didn't expect it to, but it does. So a simplified drawing of what that looks like is this, you know, from the left, you have that same fiber is still carrying the laser from the, you know, the laser light from the laser cabinet. It's very tightly wound so that as this little probe descends, that fiber is kind of like a fishing reel. It's just coming off the back end of the cryobot. The laser light, again, exits the fibers. It goes through a series of lenses. And this time, instead of the optics spreading the light onto the walls, it's very carefully shaping a beam to be injected into the ice a couple inches ahead of the nose cone. It's really focused there. And the best way to show this working is just to show this working. Hopefully these videos are going to work over Zoom. Yeah, so that little flash, if you guys are seeing it, that's not visible to the human eye. The chip in the camera can pick up that kind of purplish light. But basically, this is the fastest cryobot on Earth descending by laser. So that was kind of cool and exciting and way more fun than we thought it was going to be. With that success, we started to dig a little deeper. So this has been, you know, years of development at this point. We started to dig a little deeper, and as planetary scientists are understanding the environment a little better, we can kind of iterate with each other and figure out, you know, what are the next steps in really, you know, refining this cryobot technology. And it turns out that there are actually several different environmental regimes that you have to go through in ice on Europa. So the first is that you have to start on the surface, of course, and the surface is a pretty nasty place. It's getting hit with a ton of radiation from outer space and from Jupiter itself. Really nasty radiation environment. It's basically a vacuum. It's incredibly cold. It's like 80 degrees Kelvin. And it's, you know, brittle ice. Maybe there's like mineral deposits in there. It's not clear. That's where you have to start. Then you kind of go into the upper portion of the ice column. That's an area that's incredibly brittle. It's thought that will be like faulting and fracturing. It's still super cold. You have to look at, you know, obstacle avoidance like we've talked. Then you get down to where the ice starts to get a little warmer as you get closer to that liquid water ocean. Of course, there's a gradient from the liquid water up to the super cold surface of the ice. So as you get lower, that ice ceases to be so brittle and it becomes more of like a ductile, convecting kind of place. And what's it going to be like there? You know, how's that going to affect our strategy for getting through that kind of ice? Then you have to break through from the ice into the ocean. That's an interesting robotic operation. And then eventually, finally, you get where you always wanted to be, which is in the ocean where you get to swim around and do stuff. So we wanted to play with some of these super cold options and problems. So we built a cryo vacuum chamber in our lab in Texas, and we call this the Europa Tower. And inside this giant steampunk cylinder here, we have a cylinder of ice that is a little less than 1 meter in diameter, and it's about 2 meters high. we're able to get that thing down to 77 degrees Kelvin and get the pressure down to 10 to the -3 torr. So pretty as close a simulation to the surface of Europa as you're going to get anywhere. And so we thought, okay, now we've got this cool thing. What if we try that laser shining trick in that ice? Is it going to be any different? So this is a little kind of porthole view down into the Europa Tower with another one of these, just like we saw that direct laser probe shining direct into the ice, and then our little Lego guy for scale there. So you'll see that copper start to heat up. The thing starts to descend into the ice. You'll see this kind of snow cone developing behind it. This is a vacuum, so the ice is actually sublimating off. It's not really like melting and like kind of squirting around in there. It's just directly sublimating. Those little particles go up, they recondense, they kind of snow back down. And as the cryobot descends far enough, that hole will actually reclose. Once that hole recloses, you build up pressure, you're away from the vacuum, you can actually have liquid water again, which gets us back to the position where we can use hot water drilling again, which is what we really want for maximum efficiency. So after playing around with some tiny lasers in our big chamber, we really wanted to get back into the field and get back into something that's more of a realistic, full scale flight size cryobot. So we came up with a project called Thor. And the ultimate goal for Thor is to take it to a glacier covered volcano in Iceland. This is an incredible place that I got to go and do a field reconnaissance on. Basically, you have this Grimsvötn volcano. It's got this glacier, but it's still got a lot of hydrothermal activity going on. So you have a subglacial lake, and that's the perfect environment. We want to practice going through ice. Maybe there's sediment in that ice in Iceland, there definitely is, and then practice that breakthrough problem, and then practice how to do science operations in a subglacial lake. So Thor on the outside kind of looks similar to Valkyrie, about the same size. These things are always cylinders. Of course, the smaller the cylinder, the more efficiently it's able to travel down through the ice. I won't go into the details in the drawing here. The neat thing about Thor is this is another place where we were kind of able to be clever about our nuclear power source surrogate. So to kind of fake having a nuclear power source in this system, we built a subsystem called Hotshot, and that's basically just a novel heat exchanger. We run electric current through a conducting fluid in Hotshot, and that fluid acts as a resistor and it heats up. That hot fluid is in a closed loop, and it warms up the heat exchanger. On the other side of the heat exchanger is an open loop where meltwater from the ice is coming through that loop. It gets heated up and then it gets pushed back out the nose jet, and voila, you're back to hot water jetting using a thermal power source, which is what we'll end up doing on Europa. So we COVID kind of skunked our plans to take this to Alaska this year, but we did run some long duration tests of our prototype at our test tank in Austin over the summer. So you'll see this is normally you would see a big tank of water here. In this case, we've got it all covered up and insulated. We have a large chiller in there, and basically in the middle of August, in the middle of Austin, outside, we kept our test tank right above freezing with this giant chiller to allow the vehicle to practice running cold water and making it hot for something in the excess of 50 hours. We're hoping to get follow-on funding from NASA to kind of complete this work and eventually take the entire system to Iceland. So switching gears, we'll go on to the AUV section of what we've been working on. Stone Aerospace actually started with this AUV here called DepthX, and the target for DepthX was to explore and map cenote Zacaton. This was our first NASA project, and this is a water-filled limestone sinkhole in Tamaulipas. It's actually a complex of 4 water-filled sinkholes. These are sulfur-rich thermal springs, so this is a place where geologists were really interested in what was going on. astrobiologists were really interested in what's going on, and they needed a robot to explore it. So here we go. Since we're going into this three-dimensional environment, this was back kind of 2005, 6, 7 era, we wanted to make the AUV something like an all-seeing eyeball. So each ray that you see in this engineering drawing is actually a sonar beam path. So you're able to travel down through this three-dimensional kind of shaft, looking in all directions at once, mapping in all directions at once, and then using that map to kind of navigate its way back out. This was the first use of three-dimensional SLAM, so simultaneous localization and mapping. And the result was a map of each of the sinkholes. This was the most impressive one, Zakatone, that eventually went to a depth of 319 meters, maybe a little bit more. You can see at the bottom of that map, I'm not satisfied that it's totally closed. I'd be interested to go back with another system and explore that more. This system also had some science autonomy capability. So again, it's not enough for these robots to just kind of like explore and swim around. They need to be doing some sort of useful work down there too. So in this case, we wanted to collect samples that seemed likely to have life. And so if you are a biologist, and I am not, but I can still look at this image and say, oh, that red goopy stuff kind of looks like it's alive. But how do I know that? How are we making that decision? Well, it's a different color. So what we had the robot do is it had a full water chemistry suite on it, measuring as it went. And when it noticed a sharp change in either temperature or pH, it would say, whoa, hey, something changed in the water chemistry. It would then advance to a wall, and then it would use machine vision to look at that wall and look for changes in color. And just like we're able to look at this image and say, whoa, that looks like it's alive, the robot would say, oh, there's a change in color. I'm on a chemical gradient that seems pretty sharp. This is a good place to take a sample. And so that's exactly what it would do. It would approach the wall a little closer, snap a photo, grab a sample, and some of those samples actually turned back, returned new phyla of bacteria undiscovered previously. So pretty cool. At the conclusion of the DepthX project, we wanted to kind of continue this work, but take it under ice, making it a bit more like the under ice environment on Europa. So we teamed up with a geologist who was working with ice-covered lakes in Antarctica. And basically, the goal was to explore and map West Lake Bonny, which is a permanently ice-covered lake in the McMurdo Dry Valleys in Antarctica. We basically did some rebranding of the DepthX robot and started a project called Endurance. We used the same chassis and brains that were in DepthX, but we put in a new science payload. So in this particular case, the lake is pristine. As members of the U.S. Antarctic, or as the International Antarctic Treaty, we didn't want to disturb this lake any more than we needed to. So the idea was to drive the robot through the top several meters of the water column, but then lower this sonde payload, this water chemistry sensor, up and down at discrete stations to be able to get a full three-dimensional picture of the water chemistry without having to actually drive the entire robot up and down throughout the lake, which is A, energy inefficient, and B, stirs up all the sediment in this lake that's been undisturbed for thousands of years. So here we are delivering the system out to Lake Bonny. This is an incredible place to be working. We built a tent around the vehicle after it landed from the helicopter. Here it is ready to launch. Before each mission, we had to calibrate that chemistry sensor by lowering it down into the water and then spooling it back up. We would lower the whole vehicle through that hole and run off on a mission. In summary, we ran over 243 hours under ice in this over the course of 2 months, and covered something like 74 kilometers. Each little green spot you see is a place where we ran that water chemistry sonde up and down, and each different colored path is a different mission from a different day. The grids are 100-meter grids. The important thing here is that this this lake has been known since the golden age of polar exploration. The early guys, you know, Robert Falcon Scott, who died trying to come back from the South Pole. All those stoic characters that if you're into Arctic exploration, you hear about these guys. They knew about this lake since the 19aughts, and but we had never really known what the bathymetry of it was. Previously, if you wanted to learn something about this lake, you had to get out there with an ice fishing auger and drill a hole, and then you could take your sample, and you got one sample, and it would take you half a day. With this robot, we were able to go and map the entire thing in 3 dimensions, have every chemistry measurement, georeference, super cool stuff. One of the other goals was to kind of look at where the glacier at the head of the valley is coming into the lake. So this is kind of like a sideways slice of the cake if you're looking at the sonar data. So you're able to see the ground is in green. The grounding line is where the lake bed is touching the glacier as its glacier is coming out into the lake. This is an important thing for geologists and for folks who are studying climate change and how fast glaciers are retreating. The grounding line is a very important point. So they really wanted us to be able to identify the grounding line with endurance, and we were able to. We wanted to kind of up the game with that. With this under ice work, and so we got further funding from NASA to kind of continue. We morphed the DepthX and endurance system into something that was more hydrodynamic and much longer range. It had bigger thrusters. It had the same instrument suite, but instead of being on a little package that was spooled down from the water, this time we actually put it on the top of the vehicle because we were interested in studying the underside of the ice in greater detail. This vehicle maintained the ability to kind of stop and hover and move sideways and pitch up and pitch down, while also having a more classic AUV shape that's a bit more hydrodynamic. The whole thing also had to fit in that hole right there, which was one of our major engineering constraints. So looking kind of at the mission environment here, there's kind of 2 forms of ice in Antarctica. One is the ice shelf. This is the massive ice that's coming off of the continent and kind of slowly coming out over the sea, and that's there year to year. It doesn't break up or float away. It's persistent. And then there's the sea ice, and that's the seasonal stuff. It forms over the winter, it sticks around for a certain amount of time, and then towards the end of summer it's gone. The sea ice is much thinner, and we thought that would be a great place to drill the hole, but we really wanted to get under that thick ice, so we got as close as we could at this boundary kind of between the sea ice and the ice shelf. And the idea is that this new robot called Artemis would go through that tiny little hole, be able to map underneath all over this ice shelf, and then return very precisely to that tiny little hole. And that problem of returning very precisely to one tiny little spot was a major consideration for this project. This is a navigation deprived environment. Since you're in an overhead environment, there's no capability for the robot to kind of pop up if it gets lost and like get a GPS fix, or like send out a little beacon like, hey guys, my thingamajig broke, I'm stuck here, come get me. Like there were no options like that. This is a very committing kind of mission. So we worked a lot on return to home behavior. So we had an instrument called a USBL that was basically a pinger that helped us get back within a certain range of that hole in the ice. And then we used a visual docking sequence that looked for this lighted LED bar that we would send down. So this bar would blink at a frequency that's not found in nature. And the spacing of the LEDs was known to the robot. So we could tell like, oh, hey, that blinking, that looks like my home position. I should head for that. And then it was able to kind of correct and understand its distance and approach based on how the spacing of those LEDs appeared in its vision. This is kind of a cool video that shows the whole thing. I don't know if the sound is going to come on for it. Are you guys hearing sound with it?
Unfortunately not.
Yeah, I can see the video, but I can't hear it.
Oh, my speaker's off, that's why.
Oh,
I can hear it now.
So that was such an amazing expedition in field robotics. Really cool project. That whole thing went from nothing to to being deployed within like 18 months or something. Incredibly fast paced, crazy work. Lots of lessons learned, but the big thing is, look at this thing. It's like the size of a minivan. So it did some cool mapping. It did some cool water sampling and stuff under ice. But man, it is a pain to deploy. It is not really practical at all. And that was kind of one of the drivers for working towards Sunfish. So what we wanted to do after a couple of generations, we had DepthX, we had Endurance, we had Artemis, all of these huge systems, all of them orange, all of them wanting to explore three-dimensional environments. We really wanted to take all of that and distill it down to something that was much smaller, more custom, not just using off-the-shelf parts, but really trying to optimize a system here. And that's kind of where we've landed with Sunfish. So here's our quick little tank demo video showing just exactly how maneuverable this system is. So this is 6 degree of freedom vehicle. That little tail that you see on it is a fiber optic data tether. And we're using that to kind of keep an eye on what it's doing. It's behaving on its own though. We wanted to kind of keep this goal and theme of exploration. So as we've been developing Sunfish, we've been taking it to complex three-dimensional environments to explore and map. And one of those is Peacock Springs in Florida. Oh, the slide always skips. So Peacock Springs is a cave diving site. where folks have been exploring since, I don't know, the 80s. There's a pretty good map of the place. And so we wanted to see, in this pretty well-known environment, could sunfish actually swim around and make its own map and follow it back out in this more complex environment. But we also still wanted to be within the range of human divers to come rescue the vehicle if if something went wrong. This is testing, right? So we took this small little section of the cave. So there are kind of three elements at play here. One is obstacle avoidance, don't run into a wall. Another is exploration, try to find new places, and then try to plan your path through those places. This is kind of a video of how that comes together. The colored dots that we're seeing are sonar hits on the walls. The white rays that you're seeing are the vehicle's understanding of what space is open for it to move. So the vehicle will travel, it only has one sensor instead of myriad sensors, so it has one multi-beam sonar swath. It will spin using that precision that you saw in the test tank video. It'll spin and map the walls around it, decide what volume is open and free of obstacles, and then within that volume, it'll decide which direction to go based on its kind of understanding of where it wants to go. So in this case, we told the vehicle to travel north for 200 meters. So every time it has a decision to make, it's looking in that volume and trying to figure out which way gets it closer to north. Now on this part, it's on the return journey. On the return, it's able to use the map that it already made to return more efficiently, but it is still stopping and scanning to double check, like, hey, am I really where I think I am in this crazy place? And it was able to go out to this point 200 meters north and return home several times. This is what that 3D map came back and looked like. And if you overlay the hand-drawn map that humans have been using for decades, it's pretty spot on. I would venture to say that there's probably more error in the human map because of the nature of underwater cave survey being fairly difficult. This is kind of a cool thing. Here's one that I really enjoy. This is the first time that I really felt like a robot was helping me be in a cave. I'm a cave explorer in my own kind of in my own life and hobby. This does not appear to be going. Media not found. Okay, never mind. So this video isn't linked, but basically you can find this online. It's a fly through the cave void, and it is like you are crawling through a cave. Pretty incredible. With the successful tests at Peacock, the next step that we really wanted to do is try and take sunfish to a complex 3D underwater environment where humans hadn't been. We wanted to go to a place where there was no map and really push the limits and explore in a place where humans had never been. So kind of through other parts of my life, I became aware of this place in Africa, Dragon's Breath Cave in Namibia, and we got some grants from the National Geographic Society and some other groups to actually take sunfish to Africa and try and do this. By far the most difficult part of this project was trying to get the lithium battery shipped to a developing nation in Southern Africa. But other than that, this was a lot of fun. So we actually had 3 targets by the time we got there. The first was a place called Lake Guinness, and this was actually really similar to Zakatone, and it was kind of like our shakedown site. This is really easy access place. And beautiful photos. I'll just flip through a bunch of the photos here. Since it was a National Geographic project, we had some great photographers. So kind of set up our little mission control here. Again, that green fiber optic tether is for us to watch the behaviors as they're happening. Something interesting at Lake Guinness is that normally for the vehicle to understand where it is in 3-dimensional space, it has to have DVL lock on the floor, and the DVL is in the belly of the vehicle. If you're not familiar with what a DVL is, it's basically an array of 4 sonar beams that are kind of canted out at a slight angle, and they're measuring velocity as the vehicle's moving. So that helps lock in navigational drift. Well, in this case, Lake Guinness was out of range. The floor was out of range for the DVL, and so the robot kind of couldn't get a solid lock. And since sunfish is so maneuverable, we kind of scratched our heads for a second and thought, well, wait, there's a better way to do this. We'll just ask the vehicle to point its belly towards the wall, point that instrument towards the wall. The wall's right there. You can definitely get a lock on that and then descend that way. And these were exactly the kinds of problems we wanted to kind of test and run into. And this is the stuff that you only find when you're out field testing. So we came back with this 3-dimensional map of Lake Guinness. On the left is the profile view, as if you had sliced it in half and we're looking from the side. And then on the right is the top down. So kind of like Zakatone, successful shakedown test, kind of 3-dimensional looking map, or, map of that. Our next target was a place called Heraseed Cave. And this is basically a big shaft, that thing you kind of see in the center left, is a 120-meter pit going straight down into the earth. This is kind of all that was known. So the yellow section that you see is the air-filled portion, and then the blue is where that shaft continues down into water. And you see a bunch of question marks there. That's because nobody had any idea. This is beyond the depth that human divers can safely and reliably dive. And the chambers were so huge that you couldn't even see the walls. So these divers would go down, they'd say, I don't know, it's just pretty deep. I don't know even how big it is. I can't even see the wall, and I can't swim that far because I'm so deep, it'll wreck my decompression. So we bundled sunfish up in a rescue litter, and off we went. This is a shot of lowering the vehicle into this incredible shaft. There's me descending. I'll point out, just for fun, just to the right of me, there's a little iron ladder there. This is a well-known water source in a very, very dry part of Africa. So the original German farmers here installed that in, like, I don't know, 100 years ago. They used to go up and down on that ladder all the way down to there. So here's looking down in the shaft. You can see our little orange sunfish on the left, way, way down there. Beautiful shot at the beginning of the mission. Again, the walls just keep going straight down through the water. It's as if the water isn't there. The water's incredibly clear. Just pretty shots from inside this cave. Sunfish returning from a mission. And here's the map that came back. So the red that you're seeing is actually, you see this line that says water surface. The red above that was actually hand collected data using basically a kind of homemade LiDAR system. And then everything below that is sonar map. Incredibly exciting stuff. The big kind of blue and green chamber there was completely unexpected. We really expected the cave to kind of pinch out right at that point where it's in the middle, where it looks like it's kind of pinch closed. And right at that moment, the robot popped through into this place where the ceiling was actually out of range. That green ceiling that you see on there, we actually couldn't even see that. We had to just kind of draw it in as something. But super, super cool cave. And from there, we went on to the final challenge. Hardest cave was this place called Dragon's Breath. And pretty tiny hole to start to get the robot down into. And there had been some studies of Dragon's Breath, but again, it was one of these places where the lake in there was so huge, nobody really knew what was going on. Great shot inside this lake chamber. Getting the robot up and down through, through the cave entrance down to the lake chamber was kind of a feat of logistics. The robot barely fit through this one spot, very well padded. Again, just some pretty shots, sunfish getting ready for a mission. And that's actually our electrical engineers, also a great cave explorer, sitting there. And I think you have Bill Stone, the owner of Stone Aerospace, down in the rubber raft there. And I'm on the little platform. So just kind of a fun shot. Again, we had that fiber optic tether run all the way down to mission control, so that we could kind of observe what was happening. Running that through the cave was kind of a pain. And then here's that kind of final entry into the lake. And there we are, kind of heading off on a mission. And then we discover we have no communication to the surface. And so that kind of put everything, ground everything to a halt. We ran back up on the surface. We found where, most likely a baboon had kind of like attacked the fiber in the middle of the night. We had to, re-terminate the end of the fiber, kind of restring part of it. And we were back up and running. We actually had a little Chromebook down there, and the ubiquitous Xbox controllers that are used in robotics all the time, just to kind of get the mission started, go through the initial checklists, and then off we go. Parts of the lake are really shallow on one end, and then it goes off crazy deep. So on the left, we're looking at the plan view. So if you're looking, top down on the cave, the black outline there is that picture that you saw where you could see the lake surface. all of that vast area that you can see that it takes you 10 minutes to row across in a rowboat, that's just the little black line there. The actual footprint of the cave is much larger and descending. So on the right is the profile view. It goes down to a total depth of 205 meters water depth. And this one I really hoped was going to keep going. I really wanted this one to go for 10 kilometers and connect into Harrowseep Cave. It didn't do either of those things. It kind of just went down this gentle slope and pinched out at the bottom. But that's, that's worth knowing too. Super cool exploration, well beyond the range of human rescue. And again, just kind of the three-dimensional thing there. Okay, that's all of my stuff. Totally happy to engage in questions, and I think maybe we still have Bill on the line also. Yeah, we've still got Bill Stone on the line too. So I think we're both willing to field any questions that you guys have about this or Stone Aerospace or whatever.
First of all, that was an amazing presentation. Brenda, you can continue. I was going to ask Jonathan's question.
Yes, well, first, wow, that everything that you mentioned, oh my God, every single time that we bring like a guest speaker or I've seen a guest speaker, it always just kind of like reaffirms that, robotics is the way that I want to go. But to see that like you guys are doing not only robotics, you guys are actually going out, you guys are doing stuff, innovative stuff that like no one, I mean, I couldn't have thought about this like before I actually got into robotics. I couldn't have thought that any of this was gonna even be a thing, and to know that you guys are actually doing it just reaffirms it. That was a great presentation. Thank you. And also just we had someone, or well, actually Alex, you can say Jonathan's
yes, so
I'm so bit starstruck.
Yeah, I know that was awesome. The things that you guys do, just that looks like an amazing adventure, first of all, and just the amount of accomplishments you guys have made is all striking. But we had a question from Jonathan Hernandez, and I believe this was concerning the Artemis fish. Is it? Artemis robot. Artemis?
Yeah, Artemis, yeah.
Artemis. So it says, what kind of tools were used for the robot to recognize its home location beacon? I believe is that LED light with the space between them. Was it visualization with the camera? And if so, what kind of programs would be used for that kind of task?
Yeah, so it was, so I will upfront be super clear. Like I run all their field robotic stuff, and I am not super in depth on the software side. I'm not super in depth on the electrical side. I do some of the mechanical stuff, and I definitely wrench on the things, and I'll answer to the best of my ability, but I'm not going to be able to give you like the super like nitty gritty. So yes, it's machine vision. And we wrote all the software for it in-house. I don't know if that totally hits it. There was something like a spiral pattern. It's been this project was 2015, so I'm trying to remember now. So basically when the robot would go off on a mission, and as soon as it got clear of the hole, we would lower that blue blinking docking bar down, and attached to that there was also a little pinger, just a little passive like beep beep beep, sonar pinger that was used by the USBL. So the USBL, the main unit of the instrument, is on the robot. So when the robot goes to come back, and it's like, several kilometers out, it uses its kind of dead reckoning navigation to come back to within 1 kilometer of home. And once it's within 1 kilometer of home, it starts listening for that pinger and starts to follow that pinger, which just kind of acts like a hot and cold. Oh, you're getting closer. Oh, you're getting farther. Warmer, colder, warmer, colder. Follows that pinger back to within a certain range. And then it turns on the machine vision camera and starts looking for that blue color, B, that blinking frequency. And then once it gets close enough, then it's looking for the spacing of those LEDs. And there was something along the lines in there, maybe there's a spiral search pattern. I don't know if Bill wants to chime in with more details about that docking, return to home and docking.
You hit most of it. The navigation system is a 3-tiered design. The primary system is a dead reckoning system, as Vicki said. It uses a ring laser gyro inertial measurement unit, along with the Doppler velocity system. And we had 2 of those on the vehicle. One was up looking, and so it was tracing the underside of the ice cap. And when you have a solid surface lock, you can get accuracy down to like centimeter per second resolution and the velocity. And then we had twin depth sensors. So you can imagine the Z coordinate is being measured precisely by an instrument. The X and Y are estimated by the other 2 instruments. The IMU, as everybody knows, is a double integration to get a position. The velocity measurement, the Doppler, is only a single integration, so there tends to be less drift in the Doppler. And to give you a metric on that, it's about 0.04% of distance traveled. So in a kilometer, it would be under a meter of error. Is typical for that system, and it's dependent on the ring laser gyro to cover the orientation to a very high degree. So we use that to come back, and then when you get to about 3 kilometers or less away from the hole, you start picking up the inverted USBL. So it's for anybody who's a pilot, or if you've ever flown, it's equivalent to what is known as a VORTAC system. This was pre-GPS, but it gives you slant range and heading. And if you have that signal, and we basically know what that frequency is, it's set by the pinger, we can then navigate towards that. And then depending on the visibility of the water, which changed pretty dramatically while we were there, you could see the beacon up to 300 meters away. And as you got closer, then the machine vision algorithm would be doing a fast Fourier transform on that signal. And if it locked in at 2 hertz, which is, as Vicki said, not normal for nature, it knew that it had the spot, and then it would target towards that. And when it got within about 10 meters, it could actually resolve the spacing of the LEDs, which was 1 centimeter. And from that, you could do a parallax calculation to know what your distance is. And then from that point on, you basically simply locked onto that vector and came until the vehicle channel there captured the bar. It would then hard latch, and at that point the vehicle would shift. It would go from a horizontal attitude to a total vertical attitude, because it's 6 degrees freedom control, and then it would signal home that we could pull it up. And so the last little bit of that video she showed was the vehicle being pulled up the hole.
Jonathan says that yes, that answers his question and makes his brain very happy.
Yeah, that's awesome. Brenda, did you have a question? I had a couple questions in mind.
Yeah, I wanted to ask, so from the previous iteration of Sunfish, like, I mean, it's pretty big, and well, you guys made it so much smaller with Sunfish. The only thing that I noticed that, like, you guys compromised on was, like, that you guys only had 1 sensor. Like, what else did you have to compromise on to make it just that much smaller? Because that's a big difference.
It is. So we're able to get away from so yes, it's a bummer to not be that all-seeing eyeball anymore. But the high maneuverability of the vehicle makes up for that, right? So it's only got this one little multi-beam sonar. It's got like 120 degree beam spread, so it can kind of paint this little fan around, and it's so maneuverable that you can, like, oh, what's on the ceiling? Oh, okay, I don't know, I'll just look wherever you want to go. So we kind of solve that. It is a compromise, but we solve that. I'd say the big thing that we are working with right now is, again, it's not enough for these robots to just run around and explore and have fun. They need to do some sort of work while they're out there. And so on those other systems, a lot of the volume and the power consumption and all of that was taken up in these science payloads. So you either had water samplers or filter samplers or extra cameras or all of these things. And that's something that, as we're looking at finding new research venues for Sunfish to work in, how can we incorporate some sort of meaningful science payload into a pretty small volume at this point? We've got a little payload bay that's maybe about the size of a loaf of bread, really, and luckily everything keeps getting smaller, so we're able to kind of take advantage of that to get some of the systems smaller too. But but that is the challenge. You can't take infinite water samples. So you just have to be smarter. You have to be smarter about which samples you take and when and why. So we do a lot of work with science autonomy and like, how do you make those decisions based on the limited data you have? How do you know, like, this, if I were a human, I would take a sample right here. And so that's kind of how we're trying to work with that. But again, it's a compromise for sure.
All right, thank you.
Yeah.
So Jonathan has another question. Besides the chemistry suite and machine vision, are there any other common sensors you go to for detecting life?
Yeah, so life detection is a whole field of study in itself. You know, especially when you start to think about, like, and again, I'm not a biologist at all, but you know, it's hard enough to, you know, kind of detect life on Earth, and then how do you detect life that you've never seen before, and maybe isn't based on DNA, maybe it's based on some other kind of polymer, you know, chain molecule. So there's, so what do we got? Machine vision, we've got, let me think about how to kind of frame this. There are interesting things that happen in chemical processes with life that maybe aren't life itself, but like, how do you identify signs that life has been here? And one of those is the presence of chiral molecules. So, you know, if chemistry is just kind of going along abiotically, and there's a chiral molecule, you know, a handed molecule to be had in a world absent of life, those two percentages of, you know, the left-handed molecule and the right-handed molecule should be 50-50. And if you've got like 75-25, it's because there's some sort of little biological critter out there that one of its, like, you know, little cells or receptors or something will only accept the left-handed one. And so seeing this unequal distribution of chiral molecules is a good way to find life. There are people at Jet Propulsion Lab who are working on sensors like that, looking for yeah, so we said machine vision. So there are microscopes, there are three-dimensional microscopes that are looking for motility. There is this, you know, we work with a lot with a fellow out of, you know, Bay Area who's looking at fluorescence of proteins. So proteins will fluoresce. If you shine a certain, you know, wavelength of light on them, they'll kind of shine back at you, and you can be like, oh, there's something there, maybe. The bottom line is that, and the complicated thing is that you need an entire suite to really prove that you've found anything. So there's been a couple fits and starts where NASA has said, you know, and probably you guys, you know, this is before the time where you might remember, but there was this, you know, chunk of material that came from Mars, landed in Antarctica. They found this thing. They said, whoa, there's Martian fossils on this. This is amazing. Look at these little squiggly lines. They could only be life. And the world kind of freaked out for a hot second. And then they said, oh, wait, actually, no, we found another way to explain that. Oops, sorry. Yeah. You know, so these kind of false starts are pretty embarrassing, and we, you know, we definitely don't want that. So the accepted standard now is that you have to have multiple lines of evidence to suggest that you might be able to hypothesize potential life in a place. So so you're going to use all of these things. You're going to use machine vision. You're going to use, you know, microscope. You're going to use chiral sensing. You're going to use fluorescence. You're going to use, I don't know, Bill, you got a couple other to like.
Yeah.
We just did all these.
If you guys are really interested in a heavy read, Google Ladder of Life Detection. Ladder of Life Detection. It's a PDF. You can download it from several sources. It's pretty dense, but it'll give you an idea of the current thinking about how you would use a robotic system to potentially assess whether you have something or whether you don't. And generally it uses a sequence of instruments. The last two are the hardest ones to verify on a robotic system because it involves growth and replication of the life forms, whether they're microbial or multicellular or you know, something larger, metagenomics. And then the final one is Darwinian evolution. That's kind of like the gold standard at the top, but you're not going to see that in a robotic lifespan. So people are trying to figure out, how do you, first of all, determine what you might want to sample. And so there's a whole series of instruments that fall into the category called triaging. So you would be continuously sampling, and Vicky's infrared deep ultraviolet spectrometer is a good example of a triage instrument. It's looking for things like fluorescence in amino acids and polyaromatic hydrocarbons and things that would be associated with elements of life. And if it triggered that, then you might send it to a series of ion-specific electrodes. You might send it to a Raman spectrometer. You might send it to a 3D holographic microscope. You might send it to a chiral sensing system. And then kind of like at the end of that, about the best we can do right now is send it to a field DNA sequencer. This is stuff that's coming out of Oxford Nanopore right now with MinION type systems, which are now seeing microfluidics front ends being built for them, which means you don't have to have people preparing samples. You have the robot do the sampling. And then if you analyze that and that sequence comes out to something that's radically different from anything we know on Earth, then you've got a pretty good signal that you found something.
That's also the tricky thing. When you're looking for signs of life, you have to make sure you didn't bring it with you. Right? You have to sterilize the vehicle and make sure you don't have forward contamination. And then whatever you find, you have to run it against a all comparison of all sequences of anything it could have been that you brought with you, and make sure it's not one of those.
Yeah, that's something you don't really think about.
Yeah. It actually gets into interesting choices on the, for the people designing these systems, because the sterilization requirements are very strict, very, very strict. And so they actually limit, some of the process you have to go through. You have to either, bake these things at incredibly high temperatures, or you have to like soak them in peroxide, or shine really intense UV light on them. And there are materials that you might love to use in your system that are not going to stand up to that. So actually that planetary protection, there's actually a planetary protection officer who like comes into the process early on for these NASA projects, and you have to make some of your engineering materials choices based around what they say you're going to have to do to your poor little robot.
Yeah, it goes beyond that. For the surface of Europa, you're looking at about 4,000 rads of hard radiation during the course of a 1-month mission there. So lots of interesting engineering when you get down to actually sending a spacecraft out there. Once you get past the ice, if you're 5 meters into the ice, everything is much more cozy.
So I have a question for if you were to get, let's say, your robot like the Sunfish robot on Europa, how would you approach the pressures of the vacuum of space? What sort of approaches have you been taking to try to handle that obstacle?
Correct me if I'm wrong, Bill, but like the vacuum isn't a problem. The vacuum is only a problem for initiating melting. And it actually turns out that it's not even that much of a problem. So there was some paper that came out ages ago where I think some German researchers had what they call like a hot penny probe, where basically you just have like a slug of copper and you heat it up, and that should melt into ice, right? That should always melt. With just conceptually, we just think that way, intuitively. You put a hot chunk of copper on ice, it's going to melt down. And their study showed that if you did this in a vacuum, the actual, like the contact between the ice and the copper isn't actually really there. There actually wasn't good heat transfer in a vacuum. And so there was kind of this freak out, like, oh, you're not going to be able to initiate melting in a vacuum. And we've built our own chamber. We've done some of these tests. We found out that actually you can. It's actually not that dire. And then once you get past that, that initial stage, and you get that sublimate, those little snowflakes forming, they reclose your hole, you create pressure, then you can create your liquid water, and then you can drill. So I think that's the only problem that vacuum poses. And then as you take Sunfish down into the water, on Europa, actually, the equivalent pressure underwater there is no worse than Earth because of the size and gravity of the moon. Bill, can you give me the numbers here? I can never hold this stuff in my
Yeah,
hand.
it's slightly more. If the ice thickness is what they believe it to be right now, the best estimate is 24 kilometers plus or minus, and they're estimating below that the ocean could be 60 to 100 kilometers. So if you take the worst case scenario there, 24 plus 100, you're at about 1.6 times the hydrostatic pressure of the bottom of the Challenger Deep here on Earth. But that's a feasible design criteria to work for. And the other thing is that you don't have to build 1 atmosphere housings for a lot of this stuff. You can actually build fluid filled cavities. It's called pressure balanced oil filled. And as long as you check to make sure that your electronics chips are capable of handling that pressure, then you can do that and not worry about it. It's much more effective than building a metal housing. On Earth, basically, there's a dichotomy at about 6 kilometers where you have to switch from aluminum to titanium for pressure housings if you're going to do 1 atmosphere electronics housings. Most people go in super deep, though. They'll do oil filled.
Okay, and I have another question. When it comes to determining what surface the lander would land on, um, I'm sure you've considered this already. Would you be able to take advantage of the cracks or maybe the volcanoes? And if you were to, what would be the obstacle standing in your way from using those rather than just drilling through?
This is a huge debate within the Europa exploration community, and by far, we're not the only. We're one of the players that's been kind of in this game for the longest, but we're not the only ones. So there are folks at Jet Propulsion Lab and a couple of other places that are looking at this as well. The first step is that in 2023, 24, 25, something, there is supposed to launch a flyby mission called Europa Clipper. And actually, UT Austin is a major component of this. So Europa Clipper will be a little kind of, it's not quite orbiting because Jupiter makes things really difficult, being as big and massive and radiation intensive as it is, but it'll do kind of this series of little kind of slicey flybys around Europa and get a very high detailed, just surface imagery mapping, ice penetrating radar, various spectrometer, gravimeter, all kinds of data. The data that we have from Europa, like I've got this kind of pretty, slide or whatever, but we actually have incredibly poor data that's mostly from Voyager or something, like old spacecraft. We barely know what's on Europa. And not even most of it. There's one section that we've got in relatively higher resolution. So there's all these cracks and fissures. It's a very dynamic surface. There are plumes that have been observed by Hubble to be erupting, and there are cracks and fissures. Nobody's going to be able to do anything more than speculate until that data starts to come back from Clipper. But people already, certainly that doesn't stop people from speculating, of course. So yes, people talk about using those cracks or using those plumes, and Enceladus is another moon that has these plumes and cracks coming out. And so people talk about like, well, gosh, that already gets you part of the way down. The question is whether or not that's worth it. Because you are dealing with an active, by definition, you're going into a very active area. Why is there a crack there? Because that's like an earthquake zone. Things are faulting and shearing and moving. It's an area of activity. In the case of like one of these, cryovolcano spots, like what's to say you're not going to get blown back out? I'm kind of in the camp of I'd rather go to like the most peaceful, tranquil, like chill looking spot that's maybe on the shady side and isn't getting irradiated by Jupiter quite as hard. Like, let's just try and not make this any harder than it needs to be. Maybe we have to travel a little further through the ice, but at least we kind of know what we're dealing with. But it's just going to be waiting and to see what actually is there a little bit better. But yeah, people take different approaches for sure.
Awesome. And yeah, I can't wait to see, future images, more detailed images of Europa. I definitely want to see what it looks like. a couple more questions if you have the time. I don't want to take up too much of your time. So when it comes to the convection currents caused by Europa, would navigating through that be difficult? Wouldn't it be pushing it around? It'd be hard to like go through all those basically currents. And could
Yes.
you also take advantage of those currents in terms of generating power?
So this is where it gets really hard for my brain to kind of handle. And my training was actually in geology, you know, so I have a bachelor's in earth science and in chemistry. So when we talk about the lower region of the ice column convecting, we're talking about it in the same way that like Earth's mantle is convecting. So it's not like we're, you know, I'm a super visual person. So when I think of convecting, I think of like the kettle of water on my stove, and I can very clearly picture like this cycle of, you know, heating and flowing and moving. But in these materials that are actually solid yet kind of flowing, it becomes a really different, like, I think we don't have a good intuitive sense. So I think that convection is happening over a time scale that as humans we're not necessarily like really able to kind of picture quite as well. So for our intents and purposes, I think it's no different than kind of like a deep ice shelf here on Earth. It's still very cold. It's still ice. It's still moving a bit, but instead of shearing, you know, where we might be like snapping something, it's just kind of flowing. And even on the Matanuska Glacier, where we were working in Alaska, that ice is moving 2 meters a day. You don't really feel it. The robot didn't really notice it. I mean, on an engineering scale, you have to kind of plan for it, but I don't think it's something that's going to necessarily age you, or if you would have enough even information a priori to like, oh, well, this is kind of where the downwelling spot goes. Like, I don't know if Bill, if you've ever given this more thought.
There's a couple of very excellent papers by Sam Howe and Bob Papalardo out at JPL if you're really interested in this. But I've had discussions with Sam a couple of times on this, and it's like when they talk about convection, you're like a millennia to 10 millennia, you know, for this thing to go a kilometer. So there's lots of interesting hydrodynamic simulations that have gone on. But it's just that, it's simulation. Nobody really has any data. The one thing that is a big question though is trying to estimate what ocean currents might exist in the liquid water ocean due to tidal flexing of the ice shell by the passage of the orbit around Jupiter, which is highly eccentric. That's really what drives the energy in the silicate core and the hopes for finding hydrothermal vents. So that's a big one. Nobody knows, you know, what the chemistry of the water is down there. Nobody knows what the currents are, what the density will be. And, you know, the general thinking, at least at our shop, is that to do a proper exploration there, it's at least 2-stage. The first one is where you send a cryobot. Well, if you talk to Jim Green, who's the chief scientist for NASA, he'll tell you, like, the way NASA does things is you do a flyby, you do an orbit, you do a lander, then you do a rover. Okay, well, in the case of Europa, you got 2 more beyond that. You got a cryobot, and then you got a subsurface AUV. But the thing is, you've got to send a cryobot mission that goes through, and as Vicky pointed out earlier, there's this ice-water interface. Sounds simple, you know, but there it's not so simple, because in an ice situation, the cryobot motion is constrained. As soon as you hit open water, if you don't have what we refer to as a vertical motion control system, that's end of game. The cryobot will fall away in free fall, and you know, if you don't know what the depth is, it'll eventually crush. So the first mission really should be with an armored cryobot that can take at least 124 kilometers of European depth, and tell you what that water chemistry density, you know, the characteristics, the ocean currents over time, the variance of the currents with time. That would then give you what you need to do proper engineering for an AUV. And then you've really upped the ante, because you got to design an AUV that will fit within a flight practical cryobot. And right now, that picture that you saw of Thor, that's designed around a hot-fired built reactor that is designed for this mission. And that cryobot is only 35 centimeters in diameter. Right now, you wouldn't be able to fit sunfish in that. We'd have to shrink it, which means shrinking not only the power supplies, the electronics, the thrusters, the controls, the instrumentation, right? But also the science payload. You know, there's no sense going there if you don't have a miniaturized science payload that can do all the things that the people who are looking for life want to have in there, you know. And so it's always a Christmas tree, you know. It's a vehicle, and then, you know, it gets instruments put on it like little ornaments, and eventually you see something like Artemis, which had 100 instruments, you know, and it was 1.5 tons, and that's a non-starter. Not even the SLS Block 3 you know, launch vehicle could get anything out there.
Yeah, well, hopefully with like advancing technology today, you know, electronics gets smaller and smaller to the point you have like a small microchip that can hold, I don't know how many computations. And then one last question. This might be off topic of what you guys are really working on, but when it comes to the power source, would you be able to take advantage of Jupiter's gravitational tidal waves if you were to, like, let's say you would have a separate satellite away from the lander that could come back and forth maybe? Could it take advantage of Jupiter's tidal waves or the radiation that it emits?
Take it, Bill.
The radiation, unfortunately, is not an easy thing to deal with. In fact, it's not even an easy thing to shield against. It's the one that is really of concern is GCR, galactic cosmic radiation, and to a lesser extent, solar electrons and protons. And basically what happens is these things come in from various angles, and a certain statistical percentage of them get whipped up by the Jovian magnetosphere, kind of like a particle accelerator, and whack into the surface, right? And that's what you're trying to shield against, right? And so, you know, if you've got a 10 MeV proton, that's a tough one. You know, they're looking right now at cutting a fraction of that with about 1 inch of aluminum in what they call the vault for the Europa lander. If you're interested in that, look up Europa Lander Science Definition report by Kevin Hand. Really quite an amazing document if you really want to dig into the idea of what do you got to deal with when you're down there. But yeah, that's kind of the big one. I don't see any logical ways that you could harvest energy off any process that's going on there, and that's one of the reasons why most people that you talk to, they're ultimately going to come to the conclusion that the cryobot has to be fission powered, minimum 100 kilowatts thermal source. And if you deliver an AUV, you can potentially do that with a radiothermal generator similar to what they're using to power Curiosity and Perseverance, but smaller. That's the only way you can really guarantee your power.
Okay. How long would that last you for?
So the fission reactor will run with the fuel load that is being looked at for about 10 years, so way more than the mission length is needed. It's the power level that's needed. That's the big deal there. For the RTG, the plutonium 238 source will typically run for about 25 years. So again, you know, beyond the range of the mission. Probably the end of mission will be something like chemical corrosion of propellers and things like that, things that move underwater, or if you're super lucky, biofouling, which would be a hit. You know, nobody talks about this at NASA headquarters, but if you have a machine vision camera that's doing search for anything in front of the vehicle, and you come up with a metazoan, you know, anything bigger than a single-celled bacteria that's swimming around in the water, even if it's only 200 microns in size, you know, bingo, you've done it. You know, a video of something moving in the water is the gold standard. But I mean, everybody that I've talked to will settle for a microbe.
Yeah, we can only hope.
Yeah.
That's all the questions I have. Does anyone else have any questions?
No. Thank you so much to both of you, Vicky, Bill, for coming out.
Yeah, thank you
Um,
so much, guys. It's been an honor,
Yeah,
honestly.
that presentation just blew, I don't know about everyone else, but just it blew me away completely.
Yeah, no, you're very welcome. I'll put in a plug. We're always trying to figure out, what we're doing and what new projects and what we need in terms of, folks around the lab. But you guys aren't so far, so I'll mention that occasionally we do have student intern positions open up. And if there's interest, I assume maybe there is, I can the next time we have one of those, I can send an email out to Alex and Brenda to forward to the group for folks to apply if they have interest and skills kind of matching what we're looking for at the time. And right now we're, I was trying to push everybody in our group, like, hey, I'm gonna be talking to these, like, this group, like, do we know what we're gonna need this next summer? Like, oh, I don't know, I think we need this, I think we need, so we're still arguing about it. But anything from mechanical engineers to electrical engineers, software, just kind of integration people, hands around the lab, that kind of stuff. There's a wide range of stuff out there. And then Brenda, you did send a kind of a list of questions, and I looked through. The one thing that I'll say, when I'm looking at hiring people, of course you got to be good at what you're doing, whatever your subfield is. Like, do the thing that you're good at, but make sure that you do take that time for the life balance stuff and for pursuing your other interests, because those are the things that ultimately set you apart. So I was never trained as a robotics anything, right? But I was good at expedition work. And I had some technical background, and I had an understanding of chemistry, and a lot of drive to kind of learn the pieces that I didn't have. And that's kind of why I get to do this cool stuff, is because of those other interests. And there have been times where, Bill and I have been trying to figure out a solution to something, write a new proposal to NASA, come up with a new idea, and we'll just be blocked and blocked and blocked. You get out for a hike, or you get out for, rock climbing or a bike ride or something, and you come back and you're like, oh, I know the answer. We'll just make the robot go into an ice cave. That'll solve everything, and then all of a sudden you have this idea, and so take the time for that other stuff. It is important. So
Yeah, thank you.
Yeah.
That's always something that, just want to figure out a way to stand out to people who I'm applying to jobs for.
Yeah, yep. Be a well-rounded person. And let your energy shine through,
College students, we try our best.
I get it.
Yeah. One final thank you so much to both of you. We look forward to seeing those emails about those internships. I'm sure that everyone here is. Just thank you so much for coming out.
Yeah, you're very welcome. Have a good evening, everybody.
You too.
You too.
Bye, everyone.
Bye.
Bye.